Hey, this is Satish. Welcome to my YouTube channel. So today we're going to discuss how to build an analog PI controller. So the prototype that you see here, we'll walk through step by step of how to actually design, walk through the schematic and to build this. So if you're looking for a fundamental video on what a controller is and the theory behind this may not be the video for you. This is particularly addressing how to actually build and implement one. So let's get started. So the main functionality for this PI controller is voltage regulation. So what I mean by that is there is an internal voltage reference source in the controller, and it takes some feedback voltage from, let's say, another power electronic circuit, and by the way that the circuit is implemented, it regulates the voltage by changing the duty cycle, and that's what this PI controller does. So the functionality can be used in multiple other applications, but this is what I have used it for. So let's go through the schematic of how to actually do this. So we have three different connectors here, J1, J2, and J3. And J1 is basically the power supply connector. J2 is the feedback voltage that I talked about earlier. So from a power electronic system or any system in general, that connector is used to take the feedback voltage or the scaled feedback voltage from that system, and it takes that and then it gives that as an input to this controller here. And J3 connector is the actual output of the controller, which is a PWM signal. And you can see that the Zener diode 1N5222B is used to generate the 2.5 voltage internal reference that's used by the controller, and capacitors C7 and C8. So they're used for basically stabilizing the 5 volt supply and taking out any high frequency noise from the 5 volt supply. So I've used a couple of different ICs for this project. They're pretty simple ICs. So one of them is basically a high-speed comparator, and the other is a 5 volt or a single supply op amp that basically work together to actually get the PI controller action going. So the heart of the circuit is basically IC3 that you see on the bottom left, which is the OPA 365 IC, and this is an op amp which basically performs the proportional and integral action for the PI controller that we are trying to design. Now IC1 and 2 basically work in a fashion to create a square wave at the output of IC1 and a triangular wave at the output of IC2. And the component values that you see for the resistors and capacitors are designed such that a frequency of about 2.68 kilohertz is output at the second IC. A 5 volt supply is connected to pin number 7 for both the ICs, for IC1 and IC2. And C1 and C2 are basically capacitors that are used to take out the high frequency component from the power supply. And C3 is the capacitor that integrates the output from the square wave that you can see on the net on VSQ, which is basically a square wave output. So R2 and C3 work in a fashion to integrate that, and the output is at pin 6 of IC2, which is a triangular wave that's generated at a frequency of about 2.6 kilohertz. Now, if you wanted to change the frequency output from the oscillators of IC1 and IC2, that can be achieved by changing the values of the resistors and capacitors that are shown here. And the way to do it, you can probably find material online on how to design these oscillators, but that's beyond the scope of this video because we are focusing on PI controllers. So we're just going to use the output at pin 6 of IC2 at IC4, which I'll explain further. So the output from IC2 is routed to pin number 2 on IC4 that you can see as V triangular. So these two nets are connected together if they have the same name. Basically what IC3 does is it takes two inputs. One is the feedback voltage, which externally supplied from the user from another circuit, which we talked about earlier. If you wanted voltage regulation for a power electronic circuit, this would be the feedback voltage that you would be feeding in. And the other is the 2.5 volt reference that we created earlier from the 5 volt supply with the Zener diode, so that is connected to pin number 3 of IC3, and these resistors and capacitor values are chosen such that the integral gain is calculated by the time constant provided by capacitors C4 and R4, and the proportional gain is calculated by the ratio of R5 and R4 in the circuit. So if you do the quick calculation, it comes out that for this design, the proportional gain is about 3 and the integral gain is about 100 for these capacitors and resistor values. And the output of the PI controller from pin number 6 is routed finally to IC4, which is basically the PWM generator or the comparator. Resistors R6 and R7 are chosen such that they provide hysteresis for the final comparator circuit, which is the TLV3501, which is IC4, and the PWM output is finally taken from pin 6 of this IC. So with this schematic in action, let's see how the demo works. So I have my prototype ready. So I've already sorted in all the components, the resistors, capacitors, and the ICs and the connectors. I've also connected an external potentiometer that varies the input voltage from 0 to 5 volts. It's connected to an oscilloscope that tracks the feedback voltage as well as the output from the controller, and I have my power supply. So if I change my potentiometer values, you can see that my duty cycle changes. So if I increase my feedback voltage, you can see the duty cycle reduces. And if I decrease my feedback voltage, the duty cycle increases. So if this controller is used in a power electronic system, it would maintain output voltage by changing duty cycle. So I have exported the images from my scope to my PC so you can see the results a bit more clear. So when feedback voltage is less than 2.5 volts, as is shown here, so channel 2 is the feedback voltage, you can see that channel 1, which is the output from the controller, has pretty much a high duty cycle. So that means if it's used in a buck converter, that the PWM duty cycle would be increased and the output voltage would increase, so that output voltage is regulated. And let's go to the next case where feedback voltage increases as is shown here. So if it gets close to 2 or 2.5 volts in this case, the output duty cycle reduces and the controller maintains the value close to 2.5 as much as possible. So give this circuit a shot, build this on your own. Hopefully this video was useful to you. Thanks for watching. Bye.